Hello and welcome to podcast number 37. Picking up where we left off, last time we did hydroboration reaction. So this is what was on the screen from before. And so want to just pick up from this information. So again, we looked at it, we concluded that it was Markov-Nikov. It had no stereochemistry in this case. So I want to use this as a springboard into anti-Markov-Nikov. But before I do, just want to revisit real quickly a couple reactions. So if you were to use the same set of, or same reactant, same thing as here, but instead of using water, if we attacked with methanol, the methanol would come in just like water did before, and then you deprotonate it with an OCH3. So this can be done not only to add an OH, but to add an OR group if we wanted. And you can even do it under certain conditions to add a nitrogen, for instance. But for now, I just want to emphasize that it's still a Markov-Nikov addition. Mercury goes on first, complexes so it doesn't get rearrangement, and then the OH from water or the OR from either methanol or ethanol will come in. So just want to revisit that. So this is Markov-Nikov, but we don't always want to get Markov-Nikov addition. Sometimes we want to do a reaction where we get anti-Markov-Nikov. We want the OH to go to the less crowded. And so if you recall, the big thing, the most important thing in trying to get the regional selectivity we want, the first thing on will always choose the better carbon. So if H plus or mercury is the first thing on, it'll go there. But we can potentially have a case where it is not the first thing on. So notice this little 3 out here. The stoichiometric 3 means I'm going to use 3 of these reagents. I'll go through the mechanism of why it's 3 altogether, but let's just cut to the chase and then we'll work back and forth on the mechanism. If you look at the products from this, again, this is my less crowded carbon. Notice my less crowded carbon is the one that is getting the OH. So the OH is going on here. Also note, we now have a stereocenter here. This one's not a stereocenter because these two methyls are identical, but here I have an ethyl, an H, what it amounts to an isopropyl once we've reduced this carbon here with an H, and then an OH. So we end up with a chiral center. So this time we're going to have both regional selectivity of anti-Markov-Nikov, the OH going to the less crowded side, but we're also going to have stereochemistry. Now, again, the rule is if it adds first, it goes to the more preferable carbon. But this is going to be a unique situation where rather than one thing going on, let's say like before the H plus, followed by the next thing went on, the nucleophile, the CO minus, the water, or mercury goes on first and water, methanol, ethanol comes in second. This is a case where everything's going to add at once. The H and the placeholder that's going to eventually become the OH, which is the boron, will also add simultaneously. So now we're going to have a unique situation where if they add at the same time, they both have to add to the same side. That's what we're seeing, the H and OH both down or the H and the OH both up. So when you add 2 substituents or 2 groups simultaneously to the carbons of a double bond, you get what's known as syn addition, synonymous addition or same side addition. So syn, they'll both add to the top side or they'll both add to the back side. They'll both add bottom, both add top. So I'm going to look at the mechanism and again emphasize, because they add simultaneously, 2 situations. Number one, the H is going to go to the more crowded side because BH2, the other portion of the BH3 molecule, is going to choose the less crowded side. So BH3 chooses less, sends the boron and 2 hydrogens to the less crowded side. The H gets to the more crowded side. Okay, first one on, BH2, is really going on simultaneously with H, but the bigger thing chooses the better seat. So they add simultaneously, which allows for syn addition and the boron going to the less crowded side. Then OH minus is going to displace this boron, and we'll explain how that happens, but it's going to involve this peroxide molecule. So let's go ahead and work our way through this reaction. So regional selectivity, OH is going to the less crowded carbon, so it is known as anti-Markov-Nikov. And the stereoselectivity is a result of syn addition. The H and the OH going on simultaneously, adding to the same side. Meaning, let's say this one right here is priority 1, 2, 3, so you get an R. This one adding here would be priority 1, 2, 3. H and back, so you get an S. Because there is only one stereocenter, there are enantiomers. Whenever you have enantiomers, starting from an achiral starting material, you get a racemic mixture. You get 50% of the R, 50% of the S. So the optical rotation starts at 0 and finishes at 0. It doesn't rotate light, but it doesn't rotate light because of a racemic mixture, 50-50 mixture. Okay. The reason this is 3 is this boron, it can add one of the H's here and go on here, but it still has 2 H's. It can do it again. It has 2 more H's to do this with. And what happens is after it adds the first one, then it's a boron with a large R group. It gets way more selective because now boron has an H, and a massive group. So it will definitely choose the less crowded side the second time. And then it can even go on a third time. So it's already added 2 R groups. So it's Br2 with an H, even more massive. And so the preference is even more exaggerated. So there's an outside chance that the first one might, every now and then, maybe 1% go Markovnikov instead of anti-Markovnikov, just random probability. As it continues on, it gets less and less likely. So this is almost exclusively anti-Markovnikov. We're gonna treat it like it's 100%. So let's go ahead and look at the mechanism. Mechanisms, again, making this a really big deal because if you understand how it happens, it makes it much more clear, much more memorable of why it happens and what happens. So how it happens is our starting point. Again, the HB bond in BH3 is the active species here. It can interact with double bond where those electrons go here, these electrons go there. So it forms kind of a four-center transition state where, again, electrons are going to come out, attack boron, empty p orbital. This H then is going to coordinate. So for a brief moment, it isn't a full-fledged bond here. It isn't a full-fledged pi bond. It's not a full-fledged carbon H or carbon boron bond, but it's coordinated. So these dashed lines represent some transition state, some formation of interaction here, breaking here, and breaking there. It's going to keep on going. Those electrons move over completely, and you do end up with the H and BH adding syn. So I've shown them both adding in front. We could have just as easily shown them both adding in back. You have to pick one or the other just to make sure I do the drawing and emphasize it. But there's this one. There is also, just as likely, 50% of it is going to be H in back, BH2 in back. 50-50. I'm going to ignore that one for now and just go on with the one that's drawn. Like I said, it can happen 2 more times. So now this BH2 with an R group is really BHR bonded with an H. So the same transition we had here with an H, only now one of these H's is this bulky R group, comes in, and then it does it again. So you'll notice they all have the identical stereocenters. So the symmetry here is C3, that if you rotated this 120 degrees, all the H's land in the same spot, all the ethyls land in the same spot. So it's a little bit easier. So all those point groups you were learning something about how things rotate, this is that reason for doing it. When you start seeing transition states like this or intermediates like this, it's easier to help visualize that this has 3 things going on identical. So if I rotate 120 degrees, I keep on getting the same intermediate. Okay, so this compound now is ready to react. This boron, like I mentioned a few times, sulfur, phosphorus, and boron are oxophilic, meaning they love picking up oxygen. Sulfate's very common, phosphate's very common, borates are very common. So when we introduce an oxygen-rich compound, such as a peroxide, it can attack this boron and form these 3 R groups represent these 3 bulky R groups, and then this BO bond. OO bonds are highly unstable. Peroxides are just waiting to explode or do whatever they do. So we have this ability to now have a rearrangement. This R group, or this R group, or this R group, doesn't really matter which one, because of this negative on the boron, is free to move over, and in doing so, release that O. So when it does this, when it moves over to here, rearranges, going to kick that out, that OH minus now. So boron loses its negative. The negative's now on the OH minus. But this OH minus is now free to come in and attack a boron and release the OR. So it happens a few more times. This OR can come in, OR can come in, OR can come in. So we put this on. And then finally, the OH is free to come on. So it comes on, forms a negative, kicks out the OR. Another one comes in, kicks out the OR. Another one comes in, kicks out the OR. So this keeps on repeating itself multiple times until eventually, here's my OR minus, the one that's left. And again, it can happen 2 more times here. OH can come in. So you end up with a borate. You end up with boron with lots of oxygen, saturated with oxygen, and you end up with this species, the syn addition. It's simply a proton transfer reaction here. So I haven't shown the actual active proton being brought over, but just like here, I didn't show the loss of this proton from the peroxide either. So this peroxide here can come in and take off an H from one, have this, or I can add an H to from this. So this can be the proton source. I don't know if that makes any sense, but basically I'm just tracking my O minus here, my O minus here. They can, this is a result of losing a proton, this is a result of gaining a proton. So oftentimes these previous steps can be the same thing that result in the proton transfer in a future step. The thing that matters here is that you end up with syn addition. And again, it could have been either this stereoisomer or the other stereoisomer. Absolutely imperative you learn the nuances of this mechanism. So H and BH2 that make up BH3 go on simultaneously, so it's syn addition. H takes the more crowded seat, BH2 takes the less crowded seat, and then repeats it, so it's BRH2, then finally BR2 that react. When it finishes doing it, you end up with boron with 3 R groups, and it goes through everything in triplicate. Peroxide attacks, moves over to O, OH leaves. Another peroxide attacks, or OR is formed, OH leaves. Then a third peroxide, and then eventually hydroxides kick out a OR, hydroxide kicks out another OR, and so forth. So hopefully this mechanism makes some semblance of sense, and we're going to add it to our spider chart. So I have 2 spider charts going simultaneously if you're working through all these lectures. I have what I'm going to call the straightforward, just look at them, know what's going on there reactions. And then the ones that are a little more complex, they do things a little bit weird. So this is going to fall into our normal category. So the ones we've had so far, we've added HBr, and we also did HCl, but HX, a halo acid, in the presence of CCl4, we'll add in a Markovnikov fashion. We did that real early. And then just recently we did the sulfuric acid. We've also done oxymercuration, which does a very similar thing. I have that on the more complex spider chart, but when I add one more, that's BH3 and peroxide. And I want to give you a small hint of how we recognize it. So again, notice I've drawn both products now. So I've introduced a new chiral center in this example. So unlike the previous one where I didn't generate a chiral center, this one, because it starts out as Z, it can get these 2 chiral centers. So I want to emphasize it is anti-Markovnikov. OH goes to the less substituted carbon. So that's its regioselectivity, but it's also syn addition. They both add to the back or both add to the front, which results in predictable stereochemistry. Okay, so we're building a pretty massive chart of everything. And we're introducing this concept of stereospecific addition, where we end up with stereochemistry. So I want to continue down this pathway of syn addition, and notice that the anti-Markovnikov one from before had peroxide in it, and then noting that H, when it's bonded to something that adds at the same time, you get syn addition. We're going to run into a similar situation here. It's called hydrogenation, because we are adding hydrogen to this molecule. So hydrogenation is the addition of H2. And again, it's a same side mechanism. They're adding simultaneously. Both H's go on at the same time, so they have to go on the same side. You can't reach around this massive molecule and put one H on one side, one H on the other. They both go on top or both go on bottom. I've drawn both on bottom. I could easily have drawn both on top. There's no chiral center to worry about in this specific example, but I need to keep an open mind that if there were chiral centers forming, then I need to make note that it could be R or S at whichever chiral center you're staring at. And if it were 2, at both of them. Okay, so how does this happen? So again, no regioselectivity to consider because we're adding the same thing to both sides, and no stereochem to consider because we're not generating stereocenters. So regioselective, never is. None at any case because we're adding identical H's to both sides. In stereochemistry, not in this case, there's no stereoselectivity here. But in future reference, I need to note that syn addition, they both add at the same time. So the answer to stereoselectivity is either syn or anti, which we've done and we'll make a bigger ordeal about as we do a few more examples. And regioselectivity, Markovnikov or anti-Markovnikov. Okay, so the way this reaction works, quite interesting. The surface of the palladium, so palladium metal is a whole bunch of atoms, but on the very surface, those are my exposed ones. It helps if it's not actually pure palladium, but if you have a little palladium oxide in there, and as you'll learn with so many things in chemistry, when you dope the metal with some other material, something electron rich or electron poor, it creates kind of an internal conductive network. The more electrons are moving around, the more they can be shared in general. So a lot of times our catalysts are usually mostly the metal, but a small amount of oxide and a small amount of doped impurity. This one, I'm just going to worry about palladium surface and not going to worry about any of the other materials in there other than palladium. When H2 gas comes in, it attaches to the surface. So one might attach here, because H2, another one has to attach somewhere else. So they attach in pairs. So on the surface, you have all these H's. Now I've drawn them all pretty and lined up in an organized, I don't know, almost like a farm growing corn. But they're scattered, but the point is they're all on the surface. Now, if this was a thin film, you have them top and bottom. I'm only showing the top and assuming this is a massive surface that extends out in all directions. But focusing on just here, when the alkene comes in, the alkene is floating along. Oh, there's our alkene flying on in. It lands. These p orbitals can easily become sigmas. So this one can interact with that H, this interacts with that H. The electron density here can go into it, and the pi bond can pull back its original density. So if we think about the mechanism as the electrons going here, here, then they can pick up, and then finally here. They can pick up the H here, H there, and then palladium gets some electrons back in this exchange. So you end up, once the orbitals align, C takes the H's. I'm going to get rid of my drawing and just see it lift off. So it takes those H's, those orbitals are gone, and it moves on with them. So it's a surface reaction, and as long as I keep on keeping it saturated with H2 gas, it'll keep on saturating the surface, so there's plenty of H's. The alkene can come in and take those H's. So notice this is the same compound here. This pi bond is represented here and here. The two methyls are here and here. The ethyl and the H are here and here. Notice they've arched up a little bit. Normally they're sp2 and planar. Now these represent sp3, and you've added H's. And my orbital should be at a slight angle, and they should now be hybrids. But this is good enough. Hopefully this seems reasonable. So it adds it in a syn addition fashion where both H's go to the same side. So we're back to our spider chart. And I'm hopeful that as you keep building these, you can organize and have everything in one space. Whether you do it on your iPad or write it on paper, just make sure you have a chart. I've chosen this molecule for the center. I've chosen it because it is asymmetric. It has unequal, it has 2 R groups on one carbon, only 1 on the other in a hydrogen. And this methyl is different than the ring. This ring is different H, so it has potential to also make chiral centers. So if you want to do your own, make it so that you do generate chiral centers, and you do have the choice of Markovnikov and anti-Markovnikov to demonstrate this. So when we do hydrogenation, we're going to add H2. I chose platinum. You can also do this with palladium, like the example showed. It actually works with a series of metals, rhodium being one of them. For this class purposes, I'm probably only going to use platinum or palladium. And you're going to see other things attached to it. So you might see PTO2. You might see parentheses carbon, meaning to save money. I put the palladium on the surface of charcoal. Those don't matter. The key thing is the metal in conjunction with the H2. But it adds in a syn fashion. So they add both in back or both in front. So in your spider chart, you might want to add that there's also both going on in front as well as in back. So I'm again going to try to do just a few reactions at a time so you get them in quick bursts. Make sure you know the mechanisms for everything we just did. So it adds up really quick as you're going through them slowly and methodically, and everything's written out for you. It's easy to see that it makes sense. It's pretty. It's all wonderful. Draw every one of these mechanisms for yourself multiple times on different alkenes. Start with easy alkenes that have perfect symmetry, make them slightly asymmetric, and then just totally mess with yourself and do a massive polycyclic alkene that's just visually confusing, and see if you can see the simple reaction in the most complicated setting. So I will see you at the next podcast. Once again, thank you for listening. I hope they're helping, and see you in class. Bye.